Welcome to QHSE Talks. When people think about construction safety, they often picture visible risks, working at height, heavy equipment, or confined spaces. But one of the most dangerous hazards on any job site is often hidden in plain sight. It's beneath our feet. It's silent, unpredictable, and when it fails, it happens fast. We're talking about trenching and excavation. This is not just another technical topic. This is one of the leading causes of fatalities in construction, where a single miscalculation can turn a routine operation into a catastrophic event. Soil that looks stable can collapse without warning, and when it does, the forces involved are massive, far beyond what anyone can react to in real time. That's why this topic demands more than awareness. It demands precision. It demands calculation. It demands a clear understanding of how geometry, soil mechanics, and safety regulations come together in the real world. Because every slope you design, every angle you calculate, every ratio you apply directly determines whether that excavation remains stable or it fails. And this is where many people get it wrong. They treat it as memorization, just equations, just numbers for an exam. But in reality, these calculations represent something much more critical. They represent control over the physical behavior of the ground itself.
Which brings us to the mission for this QHSE Talks. Today, we are taking on a highly technical, incredibly demanding, and frankly, life-saving area of the ASP 11 examination blueprint.
It's a huge topic.
It really is. We are locking on to Domain 1, Topic 4. And for those taking notes, that's calculate slope angle and depth ratio for trenching and excavation.
Right.
We've got a massive stack of rigorous study guides right here on the table. I mean, we've got the official ASP blueprint.
Heavy reading.
Very heavy. We've got the BCSP, CSP preparation questions, the OSHA Construction Safety and Health Handbook, specifically subpart P, which is like the gold standard for this field.
The absolute Bible for excavation, yeah.
Yeah, along with specialized manuals covering rigging, flow rate, safety engineering calculations, all of it.
And we're going to try to synthesize all of that dense material for you today.
Here we are.
But, before we get into the actual formulas, we need to establish the reality of what we're talking about here.
Yeah, set the stage.
Right, because this isn't just about memorizing some trigonometry to check a box on a multiple choice test.
No.
This is about understanding the literal physical weight of the earth. I mean, excavation operations are almost always among the very first tasks undertaken on any construction site.
Because you literally have to move the earth before you can build anything on it.
Exactly. And accidental cave-ins, they account for a massive, vastly disproportionate number of construction site fatalities globally.
Yeah, and actually I was reading through the OSHA subpart P handbook last night, and there was a statistic that completely stopped me in my tracks.
Oh, the weight statistic.
Yes, it perfectly illustrates why this is so dangerous.
Right.
A single cubic yard of soil, right? Just a cubic yard.
Right.
It can weigh over 2,000 pounds.
2,000 pounds.
2,000 pounds.
It's crazy. That is essentially the weight of a compact car, just 1 cubic yard of dirt.
Right, a car.
Now picture a trench that's, say, 10 feet deep, 50 feet long, and 3 feet wide.
Okay.
Think about the cubic yardage suspended on either side of the workers who are standing down at the bottom of that trench.
Oh, wow.
The amount of weight looming over their heads is just astronomical. And here is the truly terrifying part, right?
What's that?
When a cave-in occurs, that weight falls with zero warning. You don't hear a creak.
No heads up.
No, you don't get a 5-second countdown. It happens in a fraction of a second.
Yeah.
And it is vastly beyond the physical capabilities of any human being to protect themselves, block it, or, fight their way out.
You're just buried under a fleet of compact cars, basically.
Exactly.
So if we're dealing with thousands upon thousands of pounds of dirt that want nothing more than to just fall into the empty space we just dug,
right?
How do we stop it? I mean, what exactly are we digging into, and how does OSHA even define the holes we're making?
Well, we stop it by understanding the physics of the hole itself. And the terminology here is critical for the exam because the physical rules actually change based on the dimensions.
Okay, so definitions matter.
They really do. First, the texts define an excavation. An excavation is the broadest term.
All right.
It's basically any man-made cut cavity, trench, or depression in the Earth's surface formed by earth removal.
Okay, let's unpack this. So if I take a shovel in my backyard and dig a hole to plant a tree, technically, by OSHA's definition, I've created an excavation.
Technically, yes, you have. But where the danger really multiplies and where the specific math from the blueprint applies is when an excavation becomes a trench.
Got it. So a trench is a specific thing.
Right, it's a very specific subcategory. The OSHA definition states that a trench is a narrow excavation made below the surface of the ground where the depth of the cut is greater than the width.
Okay, deeper than it is wide.
Yes, but here's the kicker. The width at the bottom is not greater than 15 feet.
Wait, I want to pause on that for a second. Why 15 feet?
It's a very specific number, yeah.
Why does the federal government care if the bottom is 14 feet wide versus, say, 16 feet wide? What changes at 15?
It really comes down to the physics of human escape and the concentration of lateral pressure.
Okay.
If a hole is, let's say, 30 feet wide at the bottom and a wall collapses, a worker standing in the center of that space has a geometric buffer.
Oh, I see. They have room.
Right. The soil might not even reach them, or they might have a split second to, move away from the failing faith.
Because it's a wide open space.
Exactly. But if the trench is narrow, under 15 feet, the worker is basically always in the immediate strike zone.
Yeah, there's nowhere to go.
Nowhere. The walls are close enough that a collapse on either side will instantly trap them against the opposite wall or just bury them completely. A trench creates this highly concentrated zone of danger.
Okay, that makes horrifying sense, honestly. But why do the walls fall in the first place?
Well, gravity.
Right, but I mean, if I dig a hole in solid ground, shouldn't the dirt just stay where it's been for the last 10,000 years? Like, why does it suddenly want to move?
That brings us to a really beautiful but deadly concept called the angle of repose.
Angle of repose. Okay.
Yeah. The sources define this as the natural slope that bulk materials or soils will form when they are unrestrained.
So if the angle of repose is just nature trying to balance itself, is calculating a slope basically us trying to outsmart gravity before gravity outsmarts us?
It is a great way to put it, yeah. It's gravity interacting with internal friction.
Okay.
Think about it on a granular level. Whenever you pile up bulk materials, whether that's grain in an agricultural silo, a pile of gravel, or just excavated soil, it won't ever form a perfect vertical cube, right?
Right, kind of slumps.
Exactly. The sides will slide outward and downward, but they don't flatten out completely like liquid water either.
Right, they form a pile.
Right, they stop at a specific angle. That stable slope is the angle of repose. It's nature finding its equilibrium where the internal friction of the particles is strong enough to resist the downward pull of gravity.
Oh, I see. Like if I take a cup of dry sugar and pour it onto a table, it naturally forms a little cone.
Perfect example.
And the steepness of that cone, that's the sugar's angle of repose.
Yeah, precisely. Now, flip that concept into the ground. When we dig a trench with perfectly vertical walls, we are artificially defying that rule.
They're making a wall out of something that wants to be a cone.
Exactly. We are restraining the soil's natural desire to slump down into its angle of repose.
Okay.
The danger is that we cannot predict exactly when that unrestrained vertical wall will suddenly, give up the fight against gravity and try to achieve that natural angle.
And when it gives up.
When it finally snaps back to its natural angle, that is what we call a cave-in.
Wow. And I imagine the angle of repose isn't a fixed number for all dirt, right? It's got to change depending on what's going on around the trench.
Oh, it varies wildly. You could dig a trench on a quiet Sunday morning, and the walls hold perfectly vertical because the internal friction of the soil is currently stronger than gravity.
Okay, sure.
But on Monday morning, a heavy supply truck drives by.
Right. The site wakes up.
Yeah, the ground vibrates. That vibration disrupts the friction between the soil particles, and suddenly the angle of repose shifts, and the wall violently collapses.
That is, I'm assuming there are rules about what can be parked next to a trench then.
Very strict rules.
Because if just a passing truck can cause a collapse, what happens if I park like a 30-ton excavator right on the edge of the hole?
Right. Well, that introduces the concept of surcharge loads.
Surcharge loads.
Yes. From a physics perspective, any weight you place on the surface of the ground near the edge of a trench is a surcharge load.
Okay.
That could be heavy machinery, pallets of pipes, or even all the dirt you just dug out of the hole, what the industry calls the spoils.
Wait. Just piling the dirt I removed next to the hole can cause the hole to collapse.
Absolutely, because that downward force from the pile doesn't just push straight down into the center of the earth?
It doesn't.
No. As it compresses the soil beneath it, that force radiates outward. It translates into lateral earth pressure.
Oh, lateral, so it's pushing sideways.
Right. So that heavy excavator parked on the edge is physically pushing the trench walls outward and inward toward the empty space you just created.
It's basically trying to squeeze the hole shut.
Yes, it is actively trying to blow out the side of the trench.
That's terrifying.
Yeah.
So how far back do things have to be? Like, is there a legal buffer zone?
Yes, OSHA strictly mandates what is known as the 2-foot rule. All spoils, equipment, and heavy materials must be kept at least 2 feet back from the immediate edge of the excavation.
Just 2 feet. That seems, is that enough?
It's the absolute minimum distance required to prevent that surcharge load from actively shearing the trench wall off into the void. It gives a tiny buffer.
Okay, so if gravity is constantly trying to pull these walls down and surcharge loads are trying to push them in, how do we know which dirt is going to hold its shape and which dirt is going to, instantly collapse the moment we dig it?
You have to classify the earth.
Classify.
Yeah, you cannot calculate a slope, you cannot build a shoring system, and you absolutely cannot safely put a human in a trench until you know the exact physical and molecular properties of the earth you're standing on.
Okay, so how does subpart P break that down?
According to OSHA, soil is categorized into 4 main types, and knowing these is completely critical for the ASP exam.
All right, let's hear them.
We have stable rock, Type A, Type B, and Type C.
Can we just start with the best case scenario? Like, if I'm a construction manager, I want to dig into something that isn't going to move.
Yeah.
That's stable rock, right?
Right. Stable rock is the absolute peak of stability. The text defines it as solid mineral matter that can be excavated with vertical sides and remain intact while exposed.
Like actual stone.
Yeah. Granite, sandstone. If you carve a hole in it, it acts like concrete. But practically speaking, it is incredibly rare in standard trenching.
Really?
Yeah, unless you're blasting through a mountain, you are almost always dealing with soil.
So moving down the hierarchy to the actual dirt we dig in every day, what is Type A?
Type A is highly cohesive material. This is your best case soil scenario. We're talking about clay, silty clay, sandy clay, or clay loam.
Why does clay hold together so well? What's physically happening in the dirt that makes it different from, say, beach sand?
It actually comes down to the shape of the particles and the molecular bonds.
Okay.
Sand particles, on a microscopic level, they're like tiny, jagged boulders. They stack on top of each other, but they don't stick.
Right, they just sort of rest there.
Exactly. Clay particles, on the other hand, are microscopic flat plates.
Oh, flat plates.
Yes, and when they're packed together, those flat plates have a massive amount of surface area touching one another, which creates strong electromagnetic bonds. They have incredibly high cohesion.
And the study guides mention a specific measurement for this cohesion, right?
Yeah.
Something called unconfined compressive strength.
Yes. Unconfined compressive strength is the critical metric here. It's the load per unit area at which a cylinder of soil will fail when squeezed.
When squeezed, got it.
So for Type A soil, it must have an unconfined compressive strength of 1.5 tons per square foot or greater.
Wow, 1.5 tons per square foot. That's a lot of pressure.
It is. It takes a lot of force to break those molecular clay plates apart.
But I'm guessing most construction sites aren't blessed with perfect solid clay. What's the next step down?
Next is Type B soil. This is moderately cohesive. It has an unconfined compressive strength between 0.5 and 1.5 tons per square foot.
Okay, so less than Type A, but still has some structure.
Right. This includes things like silt loam, or angular gravel. It has some internal strength, but it's much more prone to shifting and crumbling than Type A.
And then we have the bottom of the barrel.
Type C soil. This is the least stable, most dangerous category.
The worst.
Yeah. It has an unconfined compressive strength of 0.5 tons per square foot or less. We are talking about granular materials, standard gravel, sand, or loamy sand.
So basically stuff that just falls through your fingers.
Exactly. It has almost zero cohesion. It doesn't want to stick together at all. It just wants to flow.
So how do we actually measure this unconfined compressive strength in the real world? Like, if I'm the safety engineer standing in a muddy field on a Tuesday morning, I can't exactly send a jar of dirt to a laboratory and wait 2 weeks for the results while the backhoe is just idling, costing money.
Right. You don't have time for that. You don't have to. The competent person on site uses approved manual testing methods.
Manual methods.
Yeah. One common tool is a pocket penetrometer.
A pocket penetrometer. Sounds fancy.
It's actually really simple. It's a small, handheld, spring-loaded device. You literally push it into the wall of the trench, and a gauge tells you the compressive strength in tons per square foot.
Oh, nice. And what if they don't have a penetrometer handy? Can they just, feel it?
Yes. The texts explicitly allow for the thumb penetration test as an estimation method.
The thumb test.
Seriously.
If you press your thumb into the soil and it takes a significant amount of your body weight and effort just to make an indentation up to the end of your thumbnail,
Okay.
you're likely looking at type A. So it's really hard to push into.
Right. Now, if your entire thumb sinks in up to the knuckle with moderate effort, you are in type B territory.
And type C.
If your thumb just slides into the dirt easily with barely any resistance, you have type C.
That makes perfect sense. It's very tactile. So I use my penetrometer on Monday morning. The gauge reads 1.6 tons per square foot. I log it as type A soil. And we just build our safety systems around that math the rest of the week, right?
And that assumption right there is exactly how people die.
Wait, what do you mean?
You cannot classify the soil on Monday and assume the math holds up on Thursday if the environmental conditions have changed.
Oh.
Specifically, water. Water completely changes the math.
Really? Just water?
Oh, yeah. Our sources explicitly state that wet soil is soil that contains significantly more moisture than moist soil, to the point where cohesive material will begin to slump.
So if I'm the competent person on site, I can't just look at the dirt on Monday and assume the math holds up on Thursday if it rained on Wednesday, right?
Almost certainly not. Think about those microscopic flat plates of clay we talked about earlier.
The ones that stick together.
Right. When water infiltrates that soil, it wedges itself between those flat plates. It acts as a perfect molecular lubricant.
Oh, wow.
Yeah, it completely destroys the cohesion that was holding the soil together. A soil that tested as highly cohesive type A when it was dry can instantly downgrade to a flowing, catastrophic type C hazard when it's saturated.
This because of a rainstorm.
Just because of rain.
And the handbook has a really specific scenario about water, combined with vibration, doesn't it? Something about a roadway.
Yes. Imagine a trench dug near a busy roadway. You classify the soil as type B. It's moderately cohesive.
Okay.
But overnight, poor drainage causes water to accumulate behind the trench wall. Now, the soil behind that wall is saturated. It's practically acting like a fluid.
And then the morning commute starts.
Exactly. The heavy trucks start rolling down the roadway. That persistent vibration travels through the earth.
Shaking the fluid.
Yes. You now have a fluid-like, saturated soil being constantly shaken. Whatever tiny amount of cohesion was left is instantly vibrated apart.
That's a nightmare.
It is. The lateral pressure acting on the trench walls multiplies exponentially. A trench that was perfectly mathematically safe as a type B calculation on Monday is now a lethal trap by Thursday morning.
This is exactly why the text says that daily inspections are required, especially after adverse weather, particularly rain.
Exactly.
You have to constantly reevaluate the baseline data you are using for your formulas.
Absolutely. Once you have accurately and currently classified the soil, and you know without a doubt whether it's currently stable rock, type A, type B, or type C, you can finally apply the ASP blueprint formulas to determine exactly how to carve the earth safely.
Okay, so how do we carve it? What is the actual math we need to know for the exam to keep these walls from blowing out?
We use what are called maximum allowable slopes.
Maximum allowable slopes.
Yes, this is the critical mathematical core of Domain 1, Topic 4. The maximum allowable slope is defined as the steepest incline of an excavation face that is acceptable to prevent cave-ins.
Okay.
It is expressed as a ratio of horizontal distance to vertical rise, an H to V ratio.
And for the exam, you need to know the specific ratios for each of the 4 soil types. So let's break them down.
Sure. For stable rock, the allowable slope is vertical. That's a 90-degree angle.
Right.
You can dig straight down like you're cutting a cake because the rock has enough internal strength to defy gravity without assistance.
Makes sense. But for type A soil, our cohesive clay, the rules change. The maximum allowable slope is a 34-to-1 ratio. What does that actually look like visually?
It means for every 1 foot you dig down vertically, you must carve the top of the trench back horizontally by 34 of a foot.
Okay.
So if you dig 4 feet down, the top edge of the trench needs to be pushed back 3 feet from the vertical plane. When you draw a line from the top edge down to the bottom, it creates a 53-degree angle measured from the horizontal ground.
So it's like building a very steep pyramid in reverse.
Exactly. Now, moving to type B soil, our silt and angular gravel, the ratio flattens out. It becomes 1-to-1.
1-to-1.
Yeah, for every 1 foot down, you slope 1 foot back horizontally. That forms a perfect 45-degree angle.
And then we hit the nightmare soil.
Yep.
Type C, the loose sand, the gravel, the wet mud.
Right. The ratio here is 1.5-to-1. For every 1 foot of vertical depth, you have to push the top of the trench back a massive 1.5 feet horizontally.
Wow, that's wide.
It flattens the angle all the way down to 34 degrees.
Now, the study guides, specifically the BCSP, CSP preparation questions, they have all these trigonometry problems involving these angles. Tangents, sines are sines.
Lots of trade.
If I'm listening to this in my car right now, I don't have a whiteboard to write out equations. How do I visualize this math conceptually so I don't panic on the exam?
Okay, the best way to visualize it is to imagine a right triangle carved perfectly into the dirt at the edge of your trench.
Okay, I'm picturing a triangle.
The vertical wall of the trench, the depth you dug down, is the vertical leg of the triangle. The horizontal distance you stepped back at the surface to create your slope is the horizontal leg at the top.
Got it.
And the sloping wall of dirt connecting the two is the hypotenuse.
Okay, I see the triangle. The 90-degree corner is essentially in the empty air above the trench bottom, and the slope cuts diagonally down to it.
Right, and trigonometry is just the study of the relationships between the sides and angles of that triangle. For example, the tangent of an angle is simply the ratio of the length of the opposite side to the length of the adjacent side.
Right, SOH, CAH to A.
Exactly. In our trench, if we are measuring the angle down at the bottom corner of the trench, the opposite side is the horizontal setback at the top, and the adjacent side is the vertical depth.
So when the exam gives me a math problem that says, the tangent of the angle is 0.75, it's literally just telling me the ratio of the horizontal setback to the vertical depth is 0.75-to-1.
Exactly, and 0.75 is 3/4. So a tangent of 0.75 is the 34-to-1 ratio.
Which is type A soil. Yes. Which, as we just discussed, corresponds to an angle of 53 degrees. It's all the exact same data, just expressed in different mathematical languages, ratios, tangents, degrees. You just have to know how to translate them.
Here's where it gets really interesting. I want to apply this math to a real-world scenario to show just how extreme these regulations get in practice.
Let's do it.
Let's say we're digging a water line. The trench needs to be 10 feet deep to get under the frost line.
Okay, 10 feet vertical.
And let's say our competent person does the thumb test and determines we are working in type C soil. What does that 1.5-to-1 ratio actually mean for the footprint of our job site?
It demands an incredible amount of physical real estate.
Yeah.
If your vertical depth is 10 feet, and the rule is 1.5 horizontal feet for every 1 vertical foot, you multiply 10 by 1.5.
Okay, so that's 15.
That gives you 15 feet.
Meaning the top edge of the trench has to be sloped back 15 feet away from the bottom edge.
Yes, but here is the critical geometry that catches people off guard. That is 15 feet on each side of the trench.
No, on each side. Let's assume the bottom of your trench needs to be 4 feet wide to give the workers room to lay the pipe.
Right.
To slope that safely in type C soil, you need 15 feet of sloped dirt on the left, the 4-foot flat bottom in the middle, and 15 feet of sloped dirt on the right.
Wait, 15 plus 4 plus 15? Your 4-foot wide pipe trench now requires a 34-foot wide crater at the surface.
That is correct. You are obliterating 34 feet of surface area just to safely access a 4-foot work zone 10 feet down.
And this is where the theory hits the brick wall of reality. I mean, what if I'm digging this 10-foot trench in the middle of downtown Manhattan?
You're in trouble.
Right. I don't have 34 feet of real estate. I have a single lane of traffic on one side, a fiber optic line buried 2 feet to my left, and a skyscraper foundation on my right. I physically cannot carve the earth back at 34 degrees.
And that is precisely why we have engineering alternatives. When sloping or benching is physically impossible due to space constraints, we have to fight the lateral earth pressure with hardware.
Okay, so we bring in the metal.
Exactly. Specifically, we use support systems, which the industry calls shoring and shields, commonly known as trench boxes.
I've always wondered about the difference between those two. Is it just semantics, or are shoring and shielding fundamentally different concepts?
Oh, there are completely different engineering philosophies. Shoring actively supports the sides of the excavation.
Actively?
Yes. It uses structures like heavy timber framing or hydraulic aluminum cylinders to push actively against the trench walls. It creates an outward pressure that counteracts the inward lateral earth pressure.
So it's pushing back.
Right. It physically prevents the soil from moving. It stops the cave-in before it ever starts.
Okay, so shoring pushes back against the dirt. What about shielding?
Shielding is entirely passive. A trench box, which is essentially two massive steel plates held apart by heavy metal spreaders, does not prevent a cave-in.
Wait, it doesn't.
No, the soil outside the box can and will still collapse if it loses its angle of repose. But the box is engineered to be so structurally rigid that it can withstand the tremendous crushing pressure of the collapsed earth.
If a trench box is basically just a heavy-duty metal coffin with the ends knocked out, how do we know it won't just get crushed? I mean, what's the point of it if the dirt still collapses?
Think of it like the roll cage inside a professional race car.
Oh, a roll cage.
Yeah. The roll cage doesn't prevent the car from crashing into the wall. The crash still happens. The metal outside crumples.
Right.
But the roll cage is so strong that it preserves the human-sized void in the center of the destruction. A trench box does the same thing. The earth caves in and hits the steel plates, but the spreaders hold the plates apart, preserving a safe void for the workers inside the box during the cave-in.
That is an incredible visual. But going back to my crushing quotient, how do we know the box won't just crumple like a soda can under those thousands of pounds of dirt?
Yeah.
If 1 cubic yard weighs 2,000 pounds, a whole collapsed wall hitting that steel plate must generate unbelievable force.
It does, and you don't guess. You use what OSHA calls tabulated data.
Tabulated data.
Right. You can't just weld some scrap metal together and call it a trench box. Every commercial shoring system and trench shield comes with rigorous engineering tables provided by the manufacturer.
Okay, like an instruction manual.
Kind of. Those tables dictate exactly what depth and what soil type the specific piece of hardware can handle safely.
Our sources actually provide some examples of reading this tabulated data. Let's imagine an OSHA data chart for timber trenching shoring. It basically looks like a giant spreadsheet, right?
Yeah, it acts like an encyclopedia of pre-calculated structural safety. Let's say you're the competent person and you need to select shoring material for a trench in type C soil that is 13 feet deep and 5 feet wide.
Okay, 13 deep, 5 wide, type C.
And you decide your cross braces will be spaced at 6 feet horizontally and 5 feet vertically.
So I have all these variables: depth, width, soil type, brace spacing. How do I translate that into what kind of wood to buy at the lumberyard?
You cross-reference the variables on the tabulated data chart. First, you flip to the specific page for type C soil. Then you look down the y-axis for the depth row.
Right, the vertical axis.
Our trench is 13 feet deep, so we find the row labeled up to 15 feet.
Okay, so I'm on the right row. Now what?
Now you look across the x-axis for your brace spacing columns. You find the column for 6-foot horizontal spacing and the sub-column for 5-foot vertical spacing.
Just following the grid.
Exactly. Where that specific row and that specific column intersect on the grid, there will be a number. In this scenario, the table mandates an 8x8 timber.
Meaning I need solid wood beams that are 8 inches thick by 8 inches wide to hold back the dirt.
Exactly. If you try to save money and use a 6x6 or a standard 4x4 post in that 13-foot type C trench, the thousands of pounds of active lateral pressure will snap the timber like a dry twig.
Wow.
The tabulated data represents the exact structural math required to survive the dirt.
Is there a limit to the tabulated data? What if I'm digging a massive 30-foot deep foundation for a skyscraper? Can I just, look at the bottom of the chart?
No, you absolutely cannot. Our sources highlight a critical threshold in the safety regulations: 20 feet.
20 feet?
The handbook is explicit about this. Sloping or benching for excavations greater than 20 feet deep shall be designed by a registered professional engineer, or RPE.
Why 20 feet? What magically happens at 21 feet that makes the charts useless?
It's the compounding math of lateral earth pressure. The deeper you go, the pressure doesn't just add linearly, it multiplies exponentially based on the weight of the soil above it.
Right, all those cubic yards stacking up.
Exactly. Once you surpass 20 feet of depth, the forays become so immense, so incredibly complex and unpredictable that standard, generalized tables are no longer legally or physically sufficient.
So you need custom math.
The system must be custom designed, mathematically proven in written form, and stamped by a registered professional engineer who literally takes legal responsibility for the design.
There's another fascinating rule in the sources regarding these trench boxes and shoring systems. It's called the 2-foot rule. The text says that excavation of material is permitted up to 2 feet below the bottom of a support system or shield.
Which initially sounds crazy, right?
It totally sounds crazy. You are standing inside a metal box that is supposed to protect you, but you're allowed to dig the dirt out from underneath the walls of the box. If the box is what's keeping the walls from caving in, wouldn't digging below it just cause the dirt under the box to blow out?
It absolutely could, which is why there's a massive legal caveat attached to that permission. You can dig 2 feet below the box only if 2 conditions are perfectly met.
Okay, what's the first condition?
First, the structural system must have been mathematically designed to resist the forces calculated for the full depth of the trench, including that extra 2 feet of exposed dirt at the bottom.
So the box has to be strong enough to handle the pressure as if it went all the way to the floor, even though it doesn't.
Exactly.
What's the second condition?
The visual check. There can be absolutely no indications of a possible loss of soil from behind or below the bottom of the support system while the trench is open.
A loss of soil.
Yes. If you are standing in the box, digging that 2-foot hole below the steel plates, and you see soil starting to slough off or flow out from underneath the bottom edge of the box, you have instantly lost the integrity of the 2-foot rule.
Because if the soil flows out from under the box has nothing to rest on. It could sink, or worse, the earth pressure could blow out that exposed 2-foot gap at the bottom and just bury your legs.
Exactly, which requires someone to be actively watching the dirt, making these calls in real time.
Which perfectly transitions us to the human element. We have all these brilliant engineering systems, tabulated data, RPE design slopes, precise trigonometry, but all of these perfectly engineered mathematical ratios are completely useless if the human beings running the site don't follow the basic spatial rules of the excavation.
They mean nothing without enforcement.
Right. Who is actually out there enforcing this on a muddy Tuesday morning?
That is the role of the competent person. We've mentioned them a few times, but we really need to formally define the title because for OSHA, competent person isn't just a compliment you give a smart employee.
Right. It's not just, oh, Bob is competent.
No, it's a strict legal designation.
How does the text actually define it?
A competent person is an individual who is capable of identifying existing and predictable hazards in the surroundings or working conditions which are unsanitary, hazardous, or dangerous to employees.
Okay.
But here is the critical kicker that everyone misses on the exam. They must have the authorization to take prompt corrective measures to eliminate them.
Meaning they have the authority to stop work.
Yes. Absolute authority. If the company designates a highly trained safety engineer who knows every line of OSHA subpart P, but that engineer isn't legally allowed to shut down the excavator when they spot a hazard without calling the boss first, they do not meet the definition of a competent person.
Wow. So you need the knowledge and the power.
Both.
And this competent person is the one out there enforcing the hard spatial rules of the trench. Our sources lay out 4 primary spatial rules that every single listener needs to memorize right now. Let's hit Rule 1.
Rule 1, cave-in protection. Whether that is sloping the dirt back, installing hydraulic shoring, or dropping in a steel trench box, protective systems are legally mandatory at 5 feet of depth. The only exception is if you are digging in entirely solid, stable rock.
And we need to be clear about the nuance of that 5-foot threshold, right?
Yep.
Like, if your trench is 4.9 feet deep, federal regulations do not strictly mandate a protective system based on depth alone.
That's right.
So wait, what does this all mean? I can just let workers jump into a 4.9-foot trench with perfectly vertical walls and Type C sand.
Not necessarily. If the competent person examines the ground and sees an indication of a potential cave-in, maybe they see a tension crack forming on the surface or water seeping out of the wall, protection is required regardless of the depth.
Well, regardless.
Yes. The competent person can mandate a trench box for a 3-foot trench if they deem it hazardous. The 5-foot mark is simply the absolute non-negotiable threshold where the law says you must use protection no matter how safe it looks.
Okay, Rule 2 relates to getting out of the hole. A safe means of egress, which usually means a ladder, a structural ramp, or a stairway, is required at 4 feet of depth.
Notice the offset there. You need a ladder at 4 feet, but the strict mandate for a trench box doesn't kick in until 5 feet.
Right. Let me test you on this, because this feels like a trick question waiting to happen on the exam.
Oh.
Let me frame a real-world dilemma based on these exact numbers.
Go for it.
Let's say I have a trench that is exactly 4.5 feet deep. My competent person has done the penetrometer test and classified the soil as type B. There are no tension cracks, no water, no obvious hazards.
Okay, perfectly stable looking 4.5-foot trench.
Right. Do I mathematically and legally need a trench box or a 45-degree slope?
Based on a strict reading of the OSHA depth thresholds, assuming the competent person has found absolutely no indication of a cave-in hazard, no. You are at 4.5 feet, which is under the 5-foot threshold for mandatory protective systems.
But I'm over the 4-foot threshold for egress.
Exactly. So you would be legally required to provide a ladder, but you wouldn't be forced by the depth mandate to slope the walls at a 1-to-1 ratio.
Wow.
This scenario perfectly highlights the intersection of rigid mathematical guidelines and human judgment. The competent person is the bridge between the two.
And Rule 3 dictates exactly where that ladder has to go. The maximum lateral travel distance to that egress is 25 feet. If a worker is standing at the bottom of the trench, they cannot be more than a 25-foot walk from the nearest ladder.
This is critical for long excavations. If you are digging a utility trench that is 100 feet long, you can't just drop one ladder at the far end and call it compliant.
Well,
You need multiple ladders spaced out appropriately so that no matter where a worker is standing, they only have to travel 25 feet laterally to escape.
why 25 feet? Is that just an arbitrary number?
It actually goes back to the speed of a cave-in. When a trench wall fails, it fails at the speed of gravity. You cannot outrun it. If the walls start groaning or dirt starts trickling down, you have seconds to get out. A 25-foot lateral distance is considered the absolute maximum distance a human being can scramble to a ladder and climb out before the soil snaps back to its angle of repose and crushes them.
Makes sense.
You don't want your workers doing a 50-yard dash through ankle-deep mud while the walls are collapsing behind them.
No, definitely not.
Yeah.
And finally, Rule 4, which we touched on earlier with surcharge loads, the 2-foot edge clearance. Spoil piles, tools, and heavy equipment must be kept at least 2 feet back from the edge of the excavation.
The competent person is synthesizing all these numbers continuously. They check the 25-foot travel distance to the ladders. They use a tape measure to ensure the spoils are held back that full 2 feet.
A lot to manage.
It is. They verify that the ladder extends 3 feet above the landing surface, as noted in the study guides. And they inspect the physical integrity of the trench daily, especially after a rainstorm alters the moisture content and destroys the cohesion, or when heavy equipment alters the vibrational load on those fragile walls.
It is a phenomenal amount of spatial awareness, physical understanding, and dynamic mathematical calculation. And it brings us to the end of our deep analysis for this QHSE Talks on Domain 1, Topic 4. Let's run through a rapid-fire visual summary to cement these numbers and angles into your memory for the exam.
Let's review the maximum allowable slopes. Think of your geometry. Stable rock can be cut perfectly, vertical, 90 degrees.
Got it.
Type A, highly cohesive clay must be sloped at a 34-to-1 ratio, which creates a 53-degree angle.
Okay.
Type B, silt and angular gravel is a 1-to-1 ratio, perfectly splitting the difference at 45 degrees.
A 45-degree angle.
And type C, sand and wet mud is a 1.5-to-1 ratio, flattening out to a wide 34 degrees.
Remember the hard spatial rules for your job site. You need a ladder at 4 feet of depth. You mandate a protective system like shoring or a trench box at 5 feet of depth. A worker can never travel more than 25 feet laterally to reach their ladder. You must keep your heavy spoils and machinery at least 2 feet back from the edge. And any trench you dig that goes over 20 feet deep must be custom engineered by a registered professional engineer.
Exactly. Whether you are sitting in a quiet room with a calculator prepping for the ASP 11 exam, or you are standing in work boots on the muddy edge of a massive pit in the field, this math is the ultimate lifesaver.
It really is.
It is not abstract. These trigonometric ratios, the tangent calculations, and the unconfined compressive strength limits are the literal structural framework that holds back thousands of pounds of earth. We use this math to translate the unpredictable chaos of nature into secure, survivable geometry.
These numbers, the 34 degrees, the 45 degrees, the 53 degrees, the 4-foot egress rule, the 5-foot protection rule, they weren't just made up by bureaucrats in an office. They are written in blood. They are the direct historical result of analyzing those horrific instantaneous fatalities we talked about at the very beginning of the show. The math is the shield that preserves the void.
And as we wrap up, I want to leave you with a thought that isn't explicitly written in the current standard textbooks, but it builds directly on everything we've just analyzed regarding soil moisture, lateral pressure, and structural stability.
What's that?
Well, we have spent this entire QHSE Talks discussing how to calculate static mathematical slopes based on unconfined compressive strength and known environmental variables.
Right.
But consider this. As global climates shift, we are increasingly seeing unprecedented, highly localized microbursts of rain that can dump massive amounts of water in a matter of minutes.
Yeah, the weather is definitely getting wilder.
Given how rapidly we know water lubricates particles and degrades cohesive type B soil into flowing catastrophic type C fluid, will our standard static tabulated data and fixed H to V ratios remain safe enough in the coming decades?
Oh, wow.
Or will the safety engineer of the near future have to rely on real-time soil sensors and calculate dynamic fluctuating slope angles that change by the hour based on live environmental data?
That is an incredibly heavy question to carry with you onto the job site, and it perfectly challenges the illusion of our static safety tables. It brings us right back to our opening thought. Looking down into a fresh excavation is not like looking at a clean binary X-ray on a light board.
Not at all.
The Earth is alive, it's constantly shifting, and it is endlessly unpredictable. The diagnostic muddy waters are only getting murkier, and it's up to you, the competent person, to do the math that pushes back the dirt and keeps everyone safe. Thank you for joining us on this QHSE Talks. Keep learning, keep questioning, and stay safe out there.